This is Zach Henderson from Central Michigan, and with his advisor on the line here, talking about SEIR models for infectious disease prediction. And while it's in the news, it also is a personal issue for some people. So, Zach, take it away.
Thanks. Yeah, so as Brian said, I'm Zach. I'm from the math department at Central Michigan University, and I'm working with my advisor, Dr. Rakesh, who is here with us right now. And
I will disappear soon. Okay, I have another talk. I don't know, Brian. You have put both the talk at the same time.
Okay.
Okay.
sweet. Yeah, so what we'll be looking at, we'll look at a transportation-based SEIR model for infectious disease prediction. Make sure these work. There were some previous talks on different compartmental models. We're going to use a similar idea, except what we're really looking for is the network part of it. Our objectives here first is epidemic prediction, so predicting spread of disease. But in our model, using networks, we also want to get some spatial resolution to our predictions. And that's going to help us have some more informed intervention planning when we get the different locations and different predictions for those locations. So what we're going to do, we'll start by defining our SEIR model and take a look at the US air transportation network, do some preliminary data analysis, construct our model, run a few simulations, and draw some conclusions from what we get there. So to begin with, we have an SEIR model. So it looks a little bit more complicated than the common SIR model, but the fundamental idea is the same. So it's going to partition the population into one of these 5 compartments, where compartments are susceptible for the S, exposed, and then infectious and symptomatic. That's our I sub S. Otherwise, we have asymptomatic I sub A. And then we have the recovered category as R. And what we'll do is we'll start to connect a bunch of these networks or a bunch of these models together using networks to get our resolution. So to keep this in the back of our minds, this is the type of output that we're going to get using this specific type of compartmental model. And we'll analyze it a little bit after we go through what each of the model components are. The other thing about a compartmental model is the flow chart is very helpful to intuitively follow the process. But for modeling purposes, we want this set of differential equations. Here, there's going to be one differential equation for each compartment. So I have a set of 5 equations with these parameters with each of the representations here. So if we go ahead and walk through what is going to happen, when there's an outbreak of a disease, most of us are going to start in the susceptible compartment, which means we're able to contract the disease, but we need to be contacted by somebody who is infectious before we become exposed. And that type of interaction is modeled by this lambda term, which is the force of infection. And here what the force of infection represents, maybe the easiest way to think about it, is that lambda times S models the number of new exposures per unit time. And that lambda times S shows up here in our ds over dt as minus lambda S. The minus sign, the negative terms here represent individuals moving out of that said compartment. And then the positive term, this lambda S, is individuals moving into that compartment. So as we see the arrow going from S to E, we're going to move lambda S out of S and then into the E compartment. So lambda itself, that's the force of infection, which is represented by beta times I over N. Beta is some transmission rate constant that we usually try and infer from the data. I is the number of infectious individuals, where here we're going to add together our symptomatic and asymptomatic categories. And then N is going to be the total population. So what we notice, lambda times S for the number of new exposures, that means it's directly proportional to both the number of susceptible and the number of infectious. So if we consider something when beta is 0.13, that's around the parameter we're going to use later, and suppose that N is about 100,000 as a population, what we notice here is we get this type of 3D surface plot for the number of new exposures, where along this axis, if there's nobody susceptible, there's nobody to get exposed, so there's no new exposures. And same here, if there's nobody infectious, then there's nobody to pass on the disease, so there's going to be no new exposures. And we find that there's some optimal point between the number of infectious and the number of susceptibles. But realistically speaking, not that much of the population is infectious at once. So this is kind of the surface plot that we'll be considering for the most part in our models. So we talked about estimating beta, and that comes from the basic reproduction number, which is R naught. That's something that's a little bit more common in epidemiology, and it's the number of new infections from an infected individual when the population is completely susceptible. So the important part about R naught is that when R naught is greater than 1, that means the disease is growing and there's going to be an epidemic. And if R naught is less than 1, then there won't be an epidemic here. So R naught is something that tends to be estimated a lot more often than beta. And then gamma is the recovery parameter. And in this case, that's going to be estimated a little bit more often as well. We could take beta as R naught times gamma. So next, once we come in contact with somebody who's infectious and the disease gets passed to us, we end up in this exposed category, which means that we're not quite infectious yet. We're going through the latency period. However, we are going to come down with the disease and become infectious at some point. So that's modeled by this A times P and A times 1 minus P term, where here A is 1 over the latency period given in the number of days, and P is the probability of symptoms. So for those that develop symptoms, we move to the I sub S category where we're symptomatic, and then with probability P. And if you don't develop symptoms, you move to the asymptomatic category. Once we're here, when you're infectious in either of these two categories, that means you can start to expose people who are susceptible with different gamma parameters, gamma S and gamma A, since the recovery times may be a little bit different depending on whether you're symptomatic or not. And then once you recover from the symptoms, you'll move into the recovered category, which means you have some form of immunity, and you're not going to be able to get exposed once you have this immunity and have been recovered. But one thing that's a little bit different than the classical compartmental model is that we also have this waning immunity term, sigma R, where sigma R is 1 over the number of days of expected immunity. And that means that after you've recovered from the disease, your immunity is only temporary, and over time, you're going to be able to move back into the susceptible compartment and get infected again here. The last thing that's also modeled here is we don't have a closed population, so we have the births and deaths as well. So the assumption here is that those who are born are going to be born into the susceptible compartment. That's not true for every type of disease, but the idea is we're trying to model diseases that are like COVID. So in that case, we're going to assume that the births move into the susceptible compartment. And then additionally, mu is going to be the natural death rate. But perhaps if somebody is symptomatic with the disease, the death rate may be a little bit higher. So that's why this is designated as mu sub S, so it's possibly different. So going back to the example we have, this is an example of an outbreak where R naught is greater than 1. And the reason for that, the outbreak is going to occur here when the susceptible starts to drop. There's quite a bit of exposed and infectious, and that's going to move them into the recovered category. Something that we notice is the magnitude of the infectious and the exposed categories is a lot lower than that of being in the recovered. For instance, one of the reasons for this is that you may only be exposed or infectious for maybe 10 days, whereas you would have maybe 6 months of immunity, 180 days. So that's going to make the magnitudes a little bit different. The other thing is that the sigma R term replenishes S. So if you've seen different SIR models before, compartmental models, oftentimes they're going to converge to a solution, but here we see we're getting this oscillatory behavior, and the oscillatory behavior comes from this sigma R term, which is going to move people from the recovered back to the susceptible category. So something that's really interesting and helpful for modeling these equations is that we can actually take this set of equations from a compartmental model, in this case our SEIR model, and rewrite it into a matrix equation. We're here on the left-hand side, we have a column vector of each of our differentials. And then on the right-hand side, we have this column vector of our different compartments, and we can multiply it by putting all of our parameters into a matrix, where the matrix multiplication leaves us with our set of equations when we set each of the components of the vectors equal to each other. And for helpful notation, we just take dm over dt. We're calling m this vector on the left here. So dm over dt is equal to d plus f times capital M, where this is our m vector. The idea is that d is going to be all of the fixed parameters here, which is everything except the force of infection parameters, which is the minus lambda and the lambda. These get sucked into the force of infection matrix F, and we'll see why we make this distinction here when we look at the network-based model. So some limitations of the SEIR model on its own is that it gives a single estimation for whatever population we're looking at. In this case, we're looking at the United States and the different states within it. So every state has to have the same color with it, if you will, of number of infections. And there's no spatial distinction between different results here. But what we really want is we want to get multiple spatially distinct estimations. Where here, let's say I'm the governor of Michigan, maybe you're the governor of California. We want to know what's happening to our constituents rather than the country as a whole, since that might help us with our intervention planning a little bit more. So how we're going to do this is we're going to start to consider transportation networks. So a network, if you're more into pure math, it's the same thing as a graph. And the idea is that we take a look at the air transportation network. That's got the nicest data that we could find. And the air transportation network, the nodes are going to be the locations. In this case, we're considering our locations as the United States states. So we're going to have 50 nodes. Each one of those nodes has its own SEIR model associated with it. And then the edges are going to be flight connections where the edge weights are going to be given by passenger data or traveler data. And in this case, we'll see how we pre-process that down here to fit into what we want for our model. But in the bottom left-hand side here, what we see is this is the number of air passengers per month in 2020. So we just summed all the edge weights together. And we noticed that the first confirmed case was on January 21st, and immediately the amount of air traffic took a significant dip after the first case was confirmed, and then slowly started to jump back up and never returned to its pre-COVID levels, at least within 2020 here. But one other way to visualize that is with the GIF image, where we look at each month the network. And we see that the distribution of edge weights is pretty similar, except we see as a whole kind of the magnitude of the edge weights took a giant dip when we see the graph take a dip here. So this is one other way to visualize the flight network. So what we can do with any network, you can always encode it into a connectivity matrix. Here we just call it a transportation matrix because we're looking at transportation data, where each of our rows give the origin location and each of the columns give the destination location. And all the entries inside of these matrices, it's going to give the passenger data. So the pre-processed matrix, we got this from Bureau of Transportation Statistics. We had to do a little bit of pre-processing to group things together and turn it into a matrix. But this gives the number of passengers from this location to this location during the entire year of 2020. But what we wanted to do is we wanted to transform this matrix down to fit into our model. And that's going to be our matrix T, which we'll call the transportation matrix. And this is going to be the proportion of the population traveling between those two locations at any given day. Where here the negatives down the diagonal, that's going to be the proportion leaving this location. So it's just the sum of all of the other entries added up and then negated here. So now what we want to do is we want to combine these components to make the transportation model. And when we look at a transportation-based SEIR model, our goal is something like this on the right, where we're going to be able to get a choropleth map, where we're going to map the proportions of those who are infectious going from green to red, just to kind of visualize the severity of the different locations. And here that's going to be based off of this state matrix, and we'll see how we obtain this in a few slides. But the three categories of updates we have, one is going to be movement between two different states. So that's going to be with the transportation matrix. There's also progression, so progressing through the disease states, that's going to be with the D matrix from the SEIR model. And then we also have new exposures, which is going to be analogous to the F matrix from the original SEIR model. So we need 5 components for the model that we're going to put together with the network model, and that is locator and state matrices, the transportation matrix, return matrices, and the force of infection matrix, and we'll see how to kind of generate each one of these. But what this is going to give us, this is an old simulation that I had here. And this is really what we're going for, is to see the number of infectious by color running through our different location as time passes here. So to look at the locator and state matrices, to keep the notation a little bit easier to visualize, we're going to just assume that there's nobody infectious in either location. So no infectious, no recovered. So we're only looking at susceptible and exposed. And we're going to simplify it down to only 3 locations. We'll say blue is our first location, orange is our second, and green is our third. So the next idea is that we have a set of locator matrices. There's going to be one locator matrix for each population, and it keeps track of where its citizens are at. So what this is saying is the blue locator matrix, also blue, this says where are my citizens of blue? We'll look what citizens of blue are currently in blue, currently in orange, and currently in green. So how that looks, our first column is blue citizens in blue. There are 9 susceptible and 1 exposed. Blue citizens in orange, there is nobody there. And blue citizens in green, there is one susceptible and no exposed. And the same thing can be done for the locator matrix for orange and for green. And this is kind of the foundation of what our model is going to be built off of. So the next type of matrix we can get is the citizen state matrix, where the columns of the citizen state matrix are going to represent the state of the citizens of each of our locations here. So the idea is that if our citizen state matrix is M, this is what is the distribution of citizens of blue, of citizens of orange, and of citizens of green. And we can get this from summing across the citizens across all locations. So the idea to get the blue column, add together all the blue citizens no matter where they're at. Same for the orange with the orange citizens, and for the green with the green citizens here. And that can be done by summing all of the columns of the state matrix. So in this case, if we sum all columns of L sub green, we're going to get this vector here. So the next thing, I should say the citizen state matrix is important for kind of data reporting purposes. But here the current state matrix, because people are going to pass the disease to people that they're currently around. The current state matrix M prime, this is going to be important for the disease dynamics. And each of these columns are going to represent the disease state of people present in each of these locations. So what we can do, we can obtain these columns by summing together all the locator matrices. So here M prime, the first column, the blue column, is what is the distribution of people currently in blue. That is going to be 12 susceptible, 3 exposed. Currently in orange, there are 10 susceptible, no exposed, and currently in green, same thing, there are 10 susceptible, no exposed. So this is going to give the dynamics of where the disease is currently spreading. In this case, if we look at this example, it looks like there may be a new outbreak starting in blue since all of the exposed people are there. Everybody in orange and green are safe from the disease until somebody who's exposed travels backwards and starts to spread it in those locations. So the transportation model, what we can do is we can look at these 3 different components that we had mentioned earlier. The idea is we want to look at the change in disease state for each of the locator matrices individually with the 3 components, so movement, progression, and exposure. And the nice part about that is because the current state matrix is just the sum of all the locator matrices, we can get the change in the current state by just summing all of the changes of the locator matrices themselves. So for the first part, we want to take a look at the movement. And movement is based off of that transportation matrix we had mentioned at first. And it was processed to only calculate outgoing flights, so we need to look at return flights. So what we'll do is we'll take the same assumption that we use in compartmental models, that we have an exponential distribution. So we assume travel times are exponentially distributed with mean mu. And one of the helpful parts about that is that means 1 over mu travelers in each location are going to return back to their home location each day. And we can represent that by a return matrix, R sub I. There's going to be a different return matrix for each location. And the idea is the different return matrices are just have a different column as this 1 over mu column. So the idea is, as an example for R2, this second column has 1 over mu in all of the positions except the 2, 2 position. And then for the diagonal, it's minus 1 over mu. The idea is when we use this matrix multiplication, we're going to take 1 over mu of our citizens, let's say in location 1, and it's going to move them back to location 2, and then same for each of our other column vectors. So the change via movement, if we look at outbound and return as the 2 components of that, we'll get the ith column of the ith locator matrix times the ith row of T, and then we'll add that to the ith locator matrix times the ith return matrix, and that's going to represent our movement. Now, secondly, for progression, this is going to be the same type of progression and parameter matrix that we saw at the start, and that's going to be citizens progressing through the SEIR model from their own location. Since we assume all of these parameters are uniform across all locations, it's going to be the same d times L sub I that we had seen previously. So lastly, we also want to model exposure, which we're going to do through the force of infection matrix. Now, in the original SEIR model, there was a single force of infection because we're only looking at one location, but because that's dependent on the number of infectious and the total population, that force of infection is going to vary depending on where we're at. So what we want to do is we want to model this lambda j Sij, that's going to be the number of new infections each day to citizens of I who are currently located in J. And Sij is just notation to say the number of susceptibles from location I currently in J. And the idea is we want to produce this matrix which can be produced by a nice matrix multiplication, which is some positional matrix A, where we have -1 in the upper left and then a 1, times the locator matrix. Taking A times L sub I gives us our, oops, oh, wrong way. Oops. So taking A times L sub I is going to give us our terms without the lambdas, and then to get the lambda coefficients, we just multiply through by this force of infection matrix, capital lambda. So now that we stick that together, we have the change via exposure as A times L sub I times lambda, and then we can put these all together to give us our differential equation, looking at the change of each locator matrix, and then we can get the change in the state matrices based on these changes. It looks a little bit messy, but this is something that can be passed into Python quite nicely. That's what we've coded all of our simulations in here. So for the last few minutes, we can run through some simulations that we took a look at. So first one, we looked at COVID. Here, some of these parameter estimates were from the data. We have the different data sources listed at the end here. And the idea with this is that most of the data is given in a range, so you kind of have to pick the parameters that are hopefully going to fit the data the best. We also used the Google's open data for COVID to look at initial conditions, and we found that the first reported cases in that data set came from Delaware, where there were 4 reported cases at the same time. So what we can do is we can plug in these parameters to the model, and we can let it play out, which should be this video here. And notice we're going to get some spatial resolution here rather than just a single compartmental model. So this is really what we're going for here. Now, if we take a look at the kind of time series at different locations, what we notice is that in the upper right, we have the predicted versus the actual new infections. First, we're looking at Delaware, which was our epicenter. The idea is that the blue line is going to be the true data and the orange line is the predicted data from the model. And we notice here that in each of these locations, in the epicenter, we were able to detect kind of this first big spike, but we missed the second one. But for other locations, we missed the first big spike, but we predicted the second big spike here. So it's not exactly ideal, but the idea is that we're able to protect different spikes at different times. The scaled prediction, the green line, we're scaling it by the number of tests per 1,000 people that were administered at that time. And we see when we multiply it by the scaling factor of number of tests, it actually fits the like more fine trends of the data a little bit better. So that's something interesting to also consider. So secondly, for our second simulation, we just made the beta parameter a little bit larger, so the infection spread a little bit quicker just to keep the results a little bit more closer together. But we use the same initial conditions and parameters as the first simulation, but we'll take 4 different scenarios on travel reduction. And to reduce travel, all we need to do is multiply our transportation matrix by a scalar. And in this case, for the epicenter, almost nothing changed when we changed the amount of travel. The disease is still going to propagate inside of that epicenter location. But for the other locations, we see that reducing travel by kind of dampening our matrix, that is going to push back what's happening with the disease here. But it does keep the same shape, which is something that's interesting, maybe an artifact of the model, but that's something to consider as well. And then lastly, what we can do, something else, because we're able to get this spatial resolution, we can see and compare and contrast the data based on where our epicenter is. So here we have 3 runs. We set the epicenter in Alaska, Delaware, and North Dakota. And if we play each of these out, we can see kind of the differences for how the disease is going to spread across the country at any given time. So with these simulations, probably reinforces something that we could feel confident in assuming, but that the location of the epicenter is going to be important for the disease spread across the country here. So some conclusions that we have is that this type of model, if we involve a network, can provide some spatial data, visualize potential outbreak patterns, and provide specific insights for different kind of local level authorities. And as some future work, we want to refine the model parameters, which we could use machine learning to kind of fit the best parameters for that. But we'd also want to see which parameters are the most sensitive to change and Another idea would be to set a threshold for when an infection actually gets transferred between locations. So maybe it has to pass a certain threshold before it gets introduced to a new population. And then we could also account for alternate modes of transportation, which would just change by changing the matrix T. So attached with that are some references in case you're interested in some similar work. And I just want to acknowledge the Department of Mathematics for helping me work this out, for Simeode, let us present, and for Dr. Kesh for helping me through this. So thanks for coming, and is there any questions?
Thank you very much, Zach.